All right, so hello, welcome to class Tuesday, April 14th. I think I got both of those right this time, actually. So we're going to start off, first of all, just a little quick thing about grades. So it looks like you have until Friday to get grades in. That's at least what they pushed it to for the moment. So I did drop some grades just in case the grading cycle ended last week. I undropped all those grades, so if your grade changed and it went down significantly, it's because I undropped grades because people were getting work in and it made it easier to put grades in. I am going to redrop some grades again a little bit later, so if your grades suddenly dropped a lot, that's probably why. But yeah, just keep getting in your work, keep doing that, keep encouraging people around you to get in the work. It's a lot easier to justify you passing the class or having a better grade if I see a lot of work turned in. Yeah, if your grade dropped by a point, it's probably going to go back. I'm probably going to drop the same grades. It's just a lot easier putting in grades when I undrop everything. So I will redrop the grades. But yeah, keep getting your work in. If you're in, I can justify your grade. What do you mean, what about test grades? So I had dropped one of the test grades, but I undropped a test grade. I'm probably going to redrop a test grade. It's because some people are getting tests back in. But yeah, your grade is probably going to end up similar to what it was before. But again, just keep getting your work turned in. All right, so there's that, and I don't know how long they're going to open the grading cycle. There's a chance they just leave the grading cycle open till the end of the year. I don't know. We'll see. The district still hasn't gotten back to us on that. Yeah, am I missing anything on that? Yeah, so there's that. Now we'll talk about our quiz. So I decided just to give you a quiz on this. I know I didn't announce it, but I felt like it would be easier just to kind of give you a quiz over Coulomb's law and the simple methods of charging. And then we'll just kind of move on from this and then go into electrical circuits. That way, each test and quiz, we're covering a lot less material. So this is just kind of in a hope to make things a little bit more simple. So make sure you go through, take the quiz, and do all that. So let's look at the instructions for the quiz. All right. So we have this again, like last time. We have a way of randomizing all of your problems. So here we're going to be using the last 4 digits of your student ID number. And then if you have any 0 in your ID number, you're going to replace it with another non-zero number. So let's go through an example of what this would look like. Let's say I have an imaginary ID number. I don't know. 279013. All right. So I would go through and do these, but one of these numbers is causing a problem. This 0. We can't have anything that's a 0, so I'm going to have to replace that. And I also only care about my last 4. So last 4, I don't care about my first 2. All right, so get rid of the first 2 numbers from your student ID. I only care about the last 4 numbers. I have a 0 in here, so I want to replace the 0 with a non-zero number. So let's turn that 0 into something else. I already have a 1 and a 3. Let's just turn that into, let's say, a 2. So the new last 4 for me would be 9, 2, 1, 3. So 9 is going to be my A, 2 is going to be my B, 1 is going to be my C, and 3 is going to be my D. Any questions on those? Kind of see what I did there. So we ignore the first 2 digits. Then we put our last 4 digits on top of the letters. And if I have any zeros, you need to get rid of zeros. So just assign 0 to any other number from 1 to 9. Um, it would probably be best if you try to do it different than the other numbers. So I just made this into a 2 because I don't have 2 in any of the other numbers. So everyone's clear on how I got those numbers. All right, so then we're going to use these pretty much like we did for the last test. So for 1A, we have all these different values. So Q1 we see on here, Q1 is going to be equal to plus A nanocoulombs. All right, so see this, how we have plus A nanocoulombs. So again, I have A is 9 right here. So I have positive 9 nanocoulombs for charge 1. Charge 2 is going to be negative B nanocoulombs. So my B value was 2. Again, I can't have a 0, so I replace the 0 with any other number from 1 to 9. So negative 2 nanocoulombs. Mass 1 is just going to be C grams. Well, my C value was 1, so I have 1 gram. Mass 2 is going to be 2 times D grams. So 2 times D, my D value is 3. 2 times 3 is 6 grams. And then the distance between the objects is going to be 5 times C centimeters. So my C value is 1. 5 times 1 is 5 centimeters. Questions on those? Hopefully that's not too crazy. So any questions on any of your numbers or anything that's confusing on there? And if you have questions, there will be tutoring tomorrow at 2, and you can ask questions then, or you could always email me questions if you're still confused about those. So we'll go through. These are the numbers that we're going to use for the question. So charge 1 is positive 9 nanocoulombs, and it weighs 1 gram. Charge 2 is negative 2 nanocoulombs, weighs 6 grams. The center of these two objects will be 5 centimeters apart. The rest of these just follow through with those same numbers. Then we have a second part where we're talking about charging. So a metallic sphere is charged to a charge Q is A times B times C microcoulombs. Then we see if D is even, Q is positive. If D is odd, Q is negative. And then we have an identical uncharged sphere next to it. So that left sphere is the one that we're charging, the one with Q in it. And the right sphere has 0 coulombs of charge, so it has no net charge. All right, so my charge is going to be, not G, Q is going to be A times B times C microcoulombs. So my A value was 9. My B value is 2. My C value is 1. 9 times 2 times 1 is going to be 18 microcoulombs. Then I look for my value for D. So I see D is odd. So because D is odd, I look, D is odd, so charge is negative. So because my charge is negative, let's put this all together. So the charge on that left sphere is going to be negative 18 microcoulombs. So for everything on here where you see the letter Q, Q is going to be negative 18 microcoulombs. All right. Questions on that? Or is this kind of follow? It's pretty similar to the last one. And again, if you have any other questions on that, just feel free to ask them later. So everyone's good on those? I think that's all that shows up on here. All right, so you'll go through and work on it. I think I put the official due date 2 days from now. Just work on this and get this done as soon as possible. But hopefully this quiz shouldn't be so bad. And then after this, I won't quiz you on Coulomb's law or charging anymore, assuming that you do well. If everyone does poorly on this, then I'll probably go through and kind of reteach it a little bit. But yeah, so next class we can talk about simple circuits with batteries and resistors and things like that. And then there's 2 documents here. If you're going to print this out and write on it, I would suggest you use the PDF. The PDF is going to have better formatting. You could also write on this, like open it up in Google Docs or download it, put it in Word and open it and type on it. That's why I put a Word document here. If you open the Word document in Google Docs, the formatting is going to be a little bit iffy, but not terrible, not unreadable or anything. So you could do that. Or again, just like every assignment, you can just write it on paper and take a picture. No test for Coulomb. This is going to be like your test for Coulomb's law. Yeah, so dual credit, you only have 1 category for testing quizzes. It's just a big test category. So I'm going to count this as a smaller test. MST, and you actually have a quiz category, so this will count as the quiz. So this will be like the test for Coulomb's law and charging. I figure it's a little bit easier just to keep things small and moving as opposed to letting things get too big and having a real big test at the end. All right, so let's look through. You wanted to do the... Sorry, it's a little loud. Let me shut this door. There's a bunch of city workers outside, like, clearing the stuff next to the road. All right, so last class we were working on the methods of charging. We got through everything except part 6. There we are. So part 6 had all these different cans. So you were supposed to try this for homework. So if you didn't try this, I would suggest going through and trying to try them all. That's going to be the best. So you go through and try them and then check your work to see if you got the same answer as me. So let's just do 6. We'll just go through all of 6 on methods of charging. And then by the end of this, you have no excuse to get any of these wrong because I've gone through all of them. So 6.1. So we have a negatively charged balloon. And we put it next to 2 cans of Coca-Cola. So 2 metal cans. So metal is conducting. So I have can G is touching can H. Now, these are starting out neutral. What does neutral mean? Does neutral mean there's absolutely no charge? So these 2 are uncharged. First of all, what particles have charges? So 0 coulombs. So why do you say they don't? So their charges are protons and electrons. So a proton is a positive charge, and then an electron is a negative charge. So this has 0 coulombs of charge. So my net charge is 0 coulombs. Are there charges inside of these metal cans? Yes, there are charges. There are protons and electrons in here. So it's not that there's no charges. It's like you said, Vincent. For this one, if it's neutral, we have the same number of electrons and protons. So when we say no net charge or something is uncharged, we're not saying that there's no charges there. We're just saying the charges are balanced. I have the same number of protons and electrons to make this thing neutral. So uncharged, no charge, neutral doesn't, well, not no charge, uncharged or neutral or net charge is 0 coulombs doesn't mean we don't have charges. It just means we have balanced charges. All right, so we have metal cans here. We have a negative charge here. So metal means charges can move. What's the charge that actually moves? So electrons, do they get attracted or repelled by the balloon? So the electrons get repelled and pushed over here. So I end up having electrons pushed to this side. So because the electrons are pushed here, I'm left with more protons over here, positive, positive. So it's the positive didn't actually move here. The protons just got left here. But when you're drawing these, you can still kind of imagine that. You can imagine negatives get repelled over here, positives get attracted over here. It's not what's actually happening, but you can think of it that way when you're actually drawing your pictures, even though in reality the electrons get pushed over here. So when I look at this, I would see G is going to be a positive charge, and H is going to be a negative charge. And what is this called, where I have a negative charge on one side and a positive charge over here? So I have a positive side and a negative side. Or a positive pole and a negative pole. These two cans are polarized, right? So polarization, polarized. So yeah, this is polarization. These two cans have been polarized. So let's look at the next one. Yeah, pages used. So let's look at 2. Now I have negatively charged balloon here. I have my 2 cans in the middle here. I have a positive, wait, no, this is positive charged. And then I have the negative charged balloon over here. Again, these cans are starting out neutral. I have can I and can J. So positive. What gets pulled towards the positive? Again, negative pulled towards the positive. J ends up being positive. I can think of positive as getting pulled towards the negative. So negative gets pulled towards the positive. Positive gets pulled towards the negative. And then positive pushed away over here and negative pushed away over here. But again, in reality, the only things that actually move are the electrons move this way. So in reality, the negative electrons get pushed away from the negative and pulled towards the positive charge. And when the electrons move, they leave leftover protons here, which are positive. But when we're drawing these pictures, you can just think of positive gets pulled to negative, negative gets pulled to positive. All right, so again, we have here I is going to end up being negatively charged, and J is going to end up being positively charged, and this is another polarization example. What did the positive and negative be? So these two get attracted, yes. There is a force of attraction between them. But whenever I have an external charge, due to Coulomb's law is proportion is 1 over the distance squared. So it ends up where this positive charge pulls a net negative here, and then negative ends up with a net positive over here. So there is force of attraction between these. And that force of attraction is why all the charge doesn't separate. So when we look at our, like the problems we did from the textbook, like how many electrons actually moved, the number of electrons moving is just an absolute tiny fraction, like maybe 1 in a million or 1 in a billion electrons actually moves. But there is force of attraction here keeping it from all of the electrons separating. So these are attracted to each other, which means only a tiny, tiny fraction of electrons actually move. A lot of them do stay attached. So inside of the can itself, you are going to see a lot of positive, negative pairs still existing. So way more of these with positive, negative pairs still stuck together than actually end up separating. All right, 2. Wait. No, that's the second number 2. Number 3. What should be number 3 there? So now we have negative charge balloon, negative charge balloon. Now we have 3 cans. K, L, M, which is actually the abbreviation for the Dutch airline company, randomly. KLM. I think it's the Dutch airline company. KLM. So I have the negatives here. So the negative electrons get repelled. So they get pushed away from this one, they get pushed away from this one. So where are those electrons getting pushed into? Which can do the electrons get pushed to? To the middle can. So the electrons get pushed away from here into the middle. The electrons get pushed away from here into the middle. So we see the negative electrons getting pushed this way, the negative electrons getting pushed this way. So we have negative electrons getting squished into the middle can, which is leaving positives close to here, leaving the protons uncovered. Or again, just imagine positive pulled to the negative, negative get pushed away. Those negatives want to get as far away from here, but then they get kind of stuck in the middle. And so we're left over. So we have K ends up with a more positive charge. L is where those negative electrons get pushed. And M also has uncovered protons, leaving this as a positive. So this is kind of polarization. It's a little bit more complex. You still have a separation of charge. So you could kind of imagine positive, positive, negative. So a more complicated type of polarization. All right, 4. 4 is interesting. So I have a positively charged balloon here. Then I have my can here. So this is really similar to that first one where the electrons get pulled over here. All those, not all of them, but a good number of negative electrons get pulled over there. Positives pulled right here. what's different about 4 than 1, though? What's happening? You're touching your hand to it. So this is pretty much going to do what we call grounding. So when we touch our hand to it, you're not the best conductor, but you're an okay conductor. It's kind of like why people get struck by lightning. Like the lightning would rather find a better path to the ground, but if it sees you or the air, it's going to choose you over going through the air, which is why you should hopefully not be the tallest thing around during a lightning storm. Uh, Otherwise, you're probably going to get hit by lightning because you're a slightly better conductor than air is. So you're an okay conductor. Grounding. Whenever we ground things, it makes the charge neutral. So any wire that you have, I mean, you can always like do tricks, like you get on the balls of your feet and then duck down as much as possible. You want to minimize the contact you make with the ground. You can always hope that there's trees. Don't go to the trees. You have slightly better chances of getting hit by lightning than y'all do. But I know how to minimize those chances, so I might still be better off. Yeah, if there's ever a lightning storm and you feel your hair standing up, you're getting targeted by lightning. You have like anywhere from 0 to 3 seconds to act. Yeah, if you ever feel your hair stand up, get on the front of your feet, stand up, make as minimal contact with the ground, and kind of duck down, like squat as low as you can. Preferably in a ditch, a low area. And then maybe you won't get hit by the lightning, but by the time your hair's standing up, you're probably going to get hit by lightning. Yeah. So don't be in a field during a storm. All right, so grounding makes these charges neutral. But what side is the ground touched to, the positive or the negative side? Oh, I just actually read the question. You have much better chances of getting hit by lightning. So this positive side gets grounded. So we end up with something like this, where I have positive, 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 and then negatives, negatives, negatives connected to this ground right here. And those 3 lines are just a way of writing ground. So this first step, we have polarization. And then this next step, we ground. And what letter is this can? This is can N. So what's the final charge on can N? Bring back and forth to try to summon lightning. You're going to have a lot better forming a lightning rod. So grounding removes the charge, but not all of the charge. It removes the charge on the side the ground touches. If you really want to attract lightning, create a lightning rod, it's going to be something like this with a really sharp point made out of metal. Tall buildings tend to have this. But it's a sharp point where the lightning gets attracted to. Coat hangers. But you really still want the sharp point. If you ever see a skyscraper get hit, it's getting hit on the sharp point that they have for a lightning rod intentionally. So this polarization got rid of the positives, and in reality, it kind of sucked electrons out of the ground to neutralize these. But I'm still left with negatives over here on the side that wasn't grounded. So we end up with a negative charge here. In this process where we charged an object by not touching it to the charged object, this is another way of doing induction. This whole method is charging by induction. Like this whole process right here is induction. So there's a few ways of charging by induction. And I guess I should probably actually include the charge in there. Don't focus too much on that. I'm not going to go super in depth with that. In fact, you can look at the quiz and see I didn't do things with grounding or any of the crazier types of charging on there. And then finally, we have this balloon positive next to a sad, lonely can all by itself over here. It's in quarantine. All right. So again, positive here. The electrons get pulled close to it. Protons left stuck over here. Or just imagine positive repels away, negative gets attracted. So this is just polarization. So what's the net charge on the can? Yeah, this is just neutral. Neutral, or the net charge is 0 coulombs. So we have charges on either side, but this is still overall neutral. I still have the same amount of positive and negative charges. So again, if we say the object is uncharged or the object is neutral, they still have to have charges. If you have something, that something is made up of protons and neutrons, otherwise you have energy. So yeah, if it's an uncharged object, the object itself is protons, electrons, and neutrons, so it does have charges. An uncharged object just has a balanced amount of protons and neutrons. All right, so that's all of the questions for the methods of charging worksheet, so you can go through those and get that turned in. If you want additional practice on Coulomb's law, I have that other additional homework assignment with the answers posted to it. You can work through those for more help on the quiz. Were there any questions on the previous homework, the one from the textbook, or did that all go okay? Scared for the AP test. I'm about to put out a mock test for the AP test. You should take it. It's going to be mostly concepts. I don't think you should be scared for it. From what the AP test makers have been putting out, I'm trying to create a test that's similar to what they're saying it will be. Go through and look at it. I don't think you're going to be that scared of the mock test I give. Yeah, I would. If you're taking the AP test, I would suggest you do the mock AP test I put out, and I think you'll be okay. Review concepts. Um, I would look through the old AP test questions I'm posting, and I'm about to post a link with some NIMSY sessions you can look at, but it's kind of going to be different than the other things. All right, so if you're here, feel free to stick around and ask more questions. I'm just going to kind of wrap up this video so it's not too long. So a few things. Again, it looks like the grading cycle is going to be ending this Friday. So if you have any late work, get that in by the end of the week. Go through, do this quiz. Again, this is the last little bit we're going to cover on Coulomb's law. Then we're going to get into circuits. I'm going to be trying to do things like this, keeping the units kind of smaller and self-contained. So doing part of a unit, then a test or quiz, and that way you're not having to go through as much all at once. But other than that, have a nice day. Stick around if you have more questions.